Alright, let's see. We are working on chapter 59 of the Linux programming interface. Let's jump over to there and open up our progress. Today's going to be a bit of a weird day because I had an appointment at 1. They were a no-show. It's now 2:13 and I get the feeling they're going to show up at 3. Just have this feeling. So I might have to break in about 45 minutes, but I figure it's worth getting in some time while we wait for them. So let's go ahead and record. We'll just say 2:15 here, 2:15. Let's go ahead and kill that music. Alright, so this chapter is all about the internet domain sockets, which basically is TCP and UDP sockets over networks and over local host on the same machine, over a loopback interface. Let's kind of give some context on how we got to this part of the sockets. So we did an overview of sockets, which was a couple of chapters ago. This is sockets introduction, which established like the basic patterns for using sockets. And then we went straight into Unix domain sockets. I wrote an example that showed how to use the setSockOpt function, which I think is a libc function, but it might be a syscall. Let's check that out. Man, syscalls. If we search for setSockOpt, yeah, it is syscall. I think when it says see notes on IPC too, that means that all these are IPC. They're multiplexed through the IPC system call. Same thing with socket syscalls. They're multiplexed through socket call. I think that has to do with how they're implemented historically. And I think these are actual syscalls in that they have their own syscall numbers, if I'm correct. Let's go ahead and check that. Where are the syscall tables defined in what file? In Linux. We were there the other day, but I forgot where. GitHub, was it git.kernel.org Linux? Okay. So we're just gonna find. We'll find for syscall star.tbl. Yeah, and then we'll just grab for 64-bit, and I think it's this one here, the x86 64-bit table. So if we open that up and search for setSockOpt, so yeah, it is a syscall. It has its own syscall number. Give me 1 second. I need to switch back over to my stream machine because I updated it, which broke a lot of stuff because I'm on Arch. And it also reset my idle timeout, which is idle look. Yeah, so I just need to disable that. Okay. So yeah, these setSockOpt is in the syscall table. And same thing with like message send. Yeah. So these are IPC stuff. So the reason I mention that is that like you can also call socket call. Oh, IPC. Oh. That means that there is no syscall called IPC in the 64-bit syscall table. These are all the syscalls available on this platform. And IPC is not in here, and socket call is not in here. So if I quit out of this man to socket call, It has a manual page, but it's not an actual syscall. Even though there's this sys socket call here. Let's look for that. So it looks like there is this one too. Is art that was under tools, perf. So maybe look at this one. This seems a little bit more promising under Arch. Arch x86 entry syscall, yeah. And here set sock opt, but socket call is not there, and IPC is not there. Yeah, same thing. Oops, IPC, not there. So when you man to, so what is this sys socket call? I don't think this is like a thing. No wrapper for socket call, and this system uses syscall. That's fine. So if you vim up, I'm just gonna do a main real quick. Paste this stuff in here, and then we'll just say foo is equal to this. No results. Versus if we set sock opt, that one definitely has one. So it's not declared. Sys socket call is not declared in glibc, so that man page is like not exactly right. We'll just say no rm main.c. It's a rip grep for sys socket call. So it is defined in some other architectures here. Let's just do it in Arch. We'll do clear, and then we'll limit to Arch. So MIPS ARM64. Oh, interesting. But it's commented out on ARM64. Oh, x86 32-bit had it. ARM has it. I noticed that sys socket call is not present on AMD 64, but is on other architectures. What is the deal? Interesting. Register starvation on 32-bit x86. Only 6 argument registers total. is this the same for IPC? IPC syscall. Are there other syscalls that are similar? I'm gonna let that output and then I'm gonna take a quick bio break. I'll be back. All right, let's see. IPC is the same story. Old mmap, mmap2, not multiplex per se, but ABI band-aids. Let's do a rip grep for old select. Never heard of that. Compat select. Core select. That's a C, that's not a table file though. I think I'm good on that. Okay, so let's pop the stack here a few frames. So basically the syscalls that are available are actual syscall numbers, are like socket, bind, listen, connect, close, stuff like that. And that was covered mostly in the introduction. Unix domain, we used setSocOpt to be able to, or getSocOpt, I forget which one. I should probably know that. The Linux program. Grep for SocOpt. getSocOpt, yeah. So use that with pure cred to be able to do the authenticated Unix domain socket. And then we went over a chapter of fundamentals of TCP/IP networking, which was entirely review for me. So now we're getting to internet domains. So it's going to be TCP/IP, but via the socket API, not just kind of theoretical stuff. So yeah, let's do a little bit of reading here. So having looked at generic socket concepts and the TCP/IP protocol suite in previous chapters, we're now ready in this chapter to look at programming with sockets in the IPv4 and IPv6 domains. As noted in chapter 58, internet domain socket addresses consist of an IP address and a port number. Other computers use binary representation of IP addresses and port numbers. Humans are much better at dealing with names than with numbers. Therefore, we describe the technique used to identify host computers and ports using names. We also examine the use of library functions to obtain the IP addresses for a particular host name and the port number that corresponds to a particular service name. That's part of the Etsy services thing. Our discussion of host names includes a description of the domain name system, which implements a distributed database that maps host names to IP addresses and vice versa, along with a bunch of other stuff. Internet domain sockets. Internet domain stream sockets are implemented on top of TCP. They provide a reliable bidirectional byte stream communication channel. Internet domain datagram sockets are implemented on top of UDP. UDP sockets are similar to their Unix domain counterparts. But note the following differences. Unix domain datagram sockets are reliable, but UDP sockets are not. Datagrams may be lost, duplicated, or arrive in different order from that in which they were sent. Sending a Unix domain datagram socket will block if the queue of data for the receiving socket is full. By contrast, with UDP, if the incoming datagram would overflow the receiver's queue, then the datagram is silently dropped. Network byte order. This is fun. In IP addresses and port numbers are integer values. One problem we encounter when passing these values across a network is that different hardware architectures store the bytes of a multi-byte integer in different orders. As shown in figure 59.1, big endian versus little endian. So it all depends on like how you do this. Like, can I install Excalibur as an app? Let's see, Pacman Excalibur. No. All right, let's just launch a browser here. Go to excalibur.com. And sorry, make this a little bit bigger here. So little endian versus big endian. So it all depends on your perspective, because this will be byte n, and we'll say this is like in the book n plus 1, and this is byte. These are all bytes. N plus 2, and finally n plus 3. So this is the way the book represents it, which is to say a left to right ordering. But that's very like it's very much based on this directionality, left to right, is based on how we read left to right. Visually, though, I mean, you can represent this in any number of ways. Like, this is a valid representation. This is, I would argue, even more of a valid implementation. Sorry. Can I rotate these? No. I would say this is the way I visualize it in my head. Is memory starts at a base address and grows up from that. So that's common. I'm not sure if I've ever seen this in a textbook, but there's no reason why you couldn't visualize it going down as well, because we read left to right, top to bottom. So that'd be something like this. And then maybe if you're Arabic, or someone whose language is right to left, you might consider this a valid representation, where it's n plus 1, n plus 2, n plus 3, like this. So just the way that we represent a series of bytes, really the direction is arbitrary. But because we are English speakers largely in technology, or speakers of languages, readers of languages, I should say, that are left to right, top to bottom, usually that's the way we represent byte streams. So if we have like echo hello, pipe that into odd XA, you see how it's HELLO new line? And if you run Python with ordinal of 65, this is hex, so it'd be 0x65. Sorry, char, not ordinal, char. I think it's char, or CHR. There we go. So it's interesting, E is there. If we go to 68, H is over there. Isn't that funny? If we do 60, those are both L's. That's not really useful. 0A. So you can see how these are flipped. So each pair of bytes, while the ASCII representation is left to right, each pair of bytes is flipped. But then each pairing is left to right. So many different ways of like representing just a series of bytes. I wonder if I do XXD. Let's do Pac-Man XXD. I think that comes with Vim. Yeah, why don't we just go ahead and install Vim then? Sudo pacman svim. Okay. So now we have Vim. We do which. Actually, I'll do a new terminal. Which Vim. Vim is lazy Vim. Cool. Just want to make sure. But now we can do our echo into XXD. And this one has 68 on the left-hand side and 65 on the right-hand side, versus the other one, the odd, flip those. So I actually like XXD a lot better in that regard. Plus it's colored. That's cool. Okay, so that's just visually representing a byte order, but big endian versus little endian is like how that byte ordering is stored in memory or emitted onto the network. So let's go back to our diagram here. So big endian has the most significant bit at the lowest address, and the least significant bit at the highest address. Which, in my mind, big endian doesn't really make a lot of sense. This is the least address, so it should store the least significant byte, right? This is the highest address, so it should store the most significant byte. Oh no, sorry. This gets really confusing really fast. So let's take this 4-byte integer in big endian. The most significant byte, I would say, belongs at the lowest address. So big endian makes more sense to me, just numerically. Like, given that the orientation of the visualization of the bytes is arbitrary, at the lowest address, you would want to store the least significant byte. Sorry, man, I flipped twice. Because the least significant byte has, like, if you have a number that's like 1001 or 1009, we'll say, this is the least significant digit, and so that should be stored in the lowest address. So least significant byte is stored in the lowest address. So little endian byte order makes the most sense to me. Big endian byte order just seems reversed needlessly, but I think big endian might be how networks transmit. So in that situation, it's not the addresses, it's the sequence of bytes that are written to the network. And so you'd have the most significant byte be first on the network. The second significant byte be second, all the way down to the least significant byte being the last. I think that's, and then there's certain architectures that do this. I like little endian over big endian, and Intel architecture is little endian. Let's see. What architectures are little endian versus big endian? Yeah, AMD 64, ARM, RISC-V, MIPS, PowerPC, AlphaVac, Spark, everything. Big endian. And I think Linux, I remember Linus was saying something about how big endian support is not something that they're going to do for RISC-V, because it's like everything's little endian. And little endian makes more sense to my little mind. Like, why you would want to do a big endian, it just seems reversed. Not considering the ordering, the visualization ordering. When you consider it visualization ordering and you say, okay, left to right is the ordering of bytes, then it kind of does make sense to store the most significant byte on the left-hand side, because that's the way we write. So this is the most significant byte on the left-hand side, but that implies an implicit ordering, a visual ordering, I should say. Oh. Sorry about that. Someone was pounding on my door. There's a delivery driver. Scared the shit out of me. All right. So basically, big endian never really makes sense unless you're visually showing bytes in the order left to right. Then it kind of makes sense because we, in our numeric system, represent the most significant bit on the left and the least significant bit on the right. But if you represent byte orderings, bottom to top, like many textbooks do, then that kind of just goes out the window. So it's big endian only makes sense if your visual ordering of bytes is left to right. Now, if your visual ordering is right to left, totally doesn't make sense. Any other orientation that you represent them in, visually, it doesn't make sense. And visual representations, like your ordering, arbitrary ordering, you shouldn't just pick one arbitrary ordering. In my mind, the lowest byte value should have the least significant byte. And that's what little endian does. I'm repeating myself here multiple times because I'm trying to drill it into my head, because while I've encountered big endian, little endian byte ordering several times, it's like one of those things that just gets flipped in my head. Like, for most of my life, I've always thought of east as left, when on a map, east is right. Like, there's something that just like flipped in my brain where like east, just mentally, I just put that to the left, and right, west, I put to the right, even though it's completely the opposite. And it took a lot of conditioning over the years for me to flip. And even now, when I think about it, when someone says east, immediately my brain goes east is left, and then I have to remap it back to right. So similar to like cardinal directions, byte ordering is one of those things that I have to like think about, because I always get it crossed in my head. And the way I'm going to remember it from here on out is that little endian, which is the dominant byte ordering for all major architectures, is the one that naturally comes naturally to me, where the byte that is the least in its address number is also the least significant. And big endian is the byte ordering used on networks and a few niche architectures still, but those are kind of like irrelevant. It's primarily used on networking, and it only really makes sense if you imply a visual ordering of memory addresses that's left to right. Any other visual orientation, it doesn't make sense. Or numerical representation doesn't make sense. So that's how I'm saving it in my brain right now. If that makes sense. All right, let's go ahead and read the chapter here, and maybe he can have some input on this as well. So IP address and port numbers are integer values. One problem we encounter when passing these values across the network is that different hardware architectures store the bytes of a multi-byte integer in different orders. As shown in figure 59.1, architectures that store integers with the most significant byte first, i.e. a byte i.e. at the lowest memory address, are termed big endian. Those who store the least significant byte first are termed little endian. The term derives from Jonathan Swift's 1726 satirical novel Gulliver's Travels, in which the term refers to opposing political factions who open their boiled eggs at the opposite ends. The most notable example of little endian architecture is x86. Digital's VAX architecture was another historically important example, since BSD was widely used on that machine. Most other architectures are big endian. A few hardware architectures are switchable between... Most other architectures are big endian. What? Seems like from AI and from what I understand, most architectures that are well adopted or little endian. A few hardware architectures are switchable between the two formats. The byte ordering used on a particular machine is called the host byte order. Since port numbers and IP addresses must be transmitted between and understood by all hosts on a network, a standard ordering must be used. This ordering is called the network byte order. It happens to be big endian. Later in this chapter, we look at various functions that convert host names, e.g. kernel.org, and service names, e.g. HTTP, to corresponding numeric forms. These functions generally return integers in network byte order, and these integers can be copied directly into the relevant fields of a socket address structure. However, we sometimes make direct use of integer constants for IP address and port numbers. For example, we may choose a hard-code a port number into our program, specify a port number as a command line argument to a program, or use constants such as IP-adder any and IP-adder loopback when specifying an IPv4 address. These values are represented in C according to the convention of the host machine, so they are in host byte order. We must convert these values to network byte order before storing them in socket address structures. The htons, htonnel, ntos, and ntol. Okay. So it'd be H2 NS, H2NL, okay. Functions are defined typically as macros for converting integers in either direction between host and network byte order. Okay, so host to network string, host to network long. Is that what it is? Host. Huh. Okay. So host to network and then network to host. In earlier times, these functions had prototypes such as the following: unsigned long, host to long, unsigned long, host long. This reveals the origin of the function names, in this case host to network long. On most early systems on which sockets were implemented, short integers were 16 bits and long integers were 32 bits. This no longer holds true on modern systems, at least for long integers. So the prototypes given above provide a more exact definition of the types dealt with by these functions. Although these names remain unchanged, the uint16 type and uint32 type data structures are 16-bit and 32-bit unsigned integers. Strictly speaking, the use of these four functions is necessary only on systems where the host byte order differs from network byte order. However, these functions should always be used so that programs are portable to different hardware architectures. On systems where host byte order is the same as network byte order, these functions simply return their arguments unchanged. Data representation. When writing network programs, we need to be aware of the fact that different computer architectures use different conventions for represent various data types. We have already noted that integer types... Hold on, let me reread that. My mind was wandering. The sun is bleeding into my room here. I need to move my desk. It's really nice out today. So at 3 I'm probably gonna have to break, and then after that I'll probably go for a walk. So I probably will be back by like, I don't know, 4:30, something like that. Alright, so we're talking about data representation. When writing network programs, we need to be aware of the fact that different computer architectures use different conventions for representing various data types. We've already noted that integer types can be stored in big endian and little endian form. There are also other possible differences. For example, the C long data type may be 32 bits on some systems and 64 bits on others. When we consider structures, The issue is further complicated by the fact that different implementations employ different rules for aligning the fields of a structure to address boundaries on the host system, leaving different numbers of padding bytes between the fields. Yeah, that's true. Because of these differences in data representation, applications that exchange data between heterogeneous systems over a network must adopt some common convention for encoding that data. The sender must encode data according to its convention, while the receiver decodes following the same convention. The process of putting data into standard format for transmitting across the network is referred to as marshalling. Various marshalling standards exist, such as XDR, External Data Representation, ASN1, BER, Abstract Syntax Notation 1. I'm familiar with that one. Cobra and XML. I'm familiar with XML. Cobra, I'm not really familiar with, and I never heard of XDR. Typically, these standards define a fixed format for each data type, defining, for example, byte order and number of bits used, as well as being encoded in the required format. Each data item is tagged with extra fields identifying its type and possibly length. However, a simpler approach than marshalling is often employed. Encode all transmitted data in text form with separate data items delimited by a designated character, typically a new line. One advantage of this approach is that we can use telnet to debug an application. To do this, we use the following command: telnet host port. We can then type lines of text to be transmitted to the application and view the responses sent by the application. We demonstrate this technique in section 5911. The problem associated with differences in representation across heterogeneous systems does apply not only to data transfer across networks, but also data transfer across a network, but also to any mechanism of data exchange between such systems. For example, if we face the same problem when transferring files on disk or tape between heterogeneous systems, network programming is simply the most common programming context in which we are nowadays likely to encounter the issue. If we encode data transmitted on a stream socket as new line delimited text, then it is convenient to define a function such as readLine, shown in listing 59.1, where you say, hey, read me a line from this file descriptor into this buffer. Don't overflow the buffer. The readLine function reads bytes from the file referred to by the file descriptor, argument fd, until a new line is encountered. The input byte sequence is returned in the location pointed to by buffer, which must point to a region of at least n bytes of memory. The return string is always null terminated, thus at most n minus 1 bytes of actual data will be returned. On success, readLine returns the number of bytes of data placed in the buffer. The terminating null byte is not included in this count. That's pretty natural. So this just goes on to define that. It's not super. Let's go and read over it, why not? So prototype we understand. If n is less than or equal to 0 or the buffer is null, then we got invalid arguments here. We declare a assigned size t numRed to tRed, total red, the buffer char buff, and character ch. So the buff currently points to the buffer. We convert to a char because pointer arithmetic is not defined on void star. Once it's a character buffer, char buffer, we set our toRead equals 0. We go into infinite loop, and then we do a read on the FD into ch, which is just one character, and we say we're going to read one character. Because we have to read character by character until we hit the new line. If numRed is -1, then we have to handle the error case. If it is interrupted, then we just continue the loop and reread it. Else, it's not an error case. And if num_rem is equal to 0, then we hit EOF and we can just return the EOF. We just say, hey, we read 0 bytes. If we else we break down to here, we write our 0 byte and we return the total read. Here, so num read is not 0. We didn't hit EOF. We're in the middle of reading, and we say, hey, if my total read is less than n minus 1, wait a minute, total read, where's total read's being returned here? Where's it being incremented here? So the first go around, total read's gonna be 0, n's gonna be like 100. So total read's gonna be increased. And at some point, total read is gonna be, say, like a 500,000, and n is 100. And so it's not gonna say that. I don't understand. Oh, because n is the total size here. It's not the num read. Usually n is used for num read here. That's why I was confused. Okay, so we're saying if total read is less than that, because we're just doing one character at a time, we increment it. We increment our pointer. And it's a post increment, so that means that we assign the character into the buffer and then we increment the pointer. And then if character is new line, we break. And then we get our 0 and we return. Okay. Pretty straightforward. It's 3 o'clock. Where are these dudes? Where are these dudes? Huh. They're supposed to be here at 1. It's now 3. Okay. Let's just finish this section here. If the number of bytes read before a new line is encountered is greater than or equal to n minus 1, then the readLine function discards excess bytes, including the new line. If the new line was read within the first n minus 1 bytes, then it is included in the return string. Thus, we can determine if bytes were discarded by checking if a new line precedes the terminating null byte in the return buffer. We take this approach so that application protocols that rely on hanging input in units of lines don't end up processing a long line as though it were multiple lines. This would likely break the protocol, as the applications on either end would become desynchronized. An alternative approach would be have readLine read only sufficient bytes to fill the supplied buffer, leaving any remaining bytes up to the next new line for the next call to readLine. In this case, the caller of readLine would need to handle the possibility of a partial line being read. We employ the readLine function in this example program presented in section 5911. So if we go back to the source code here, the discard happens here. Why does it say discard? It doesn't really do a discard though. I guess, yeah, if both of these fail, then it's just reading and discarding. Okay, I get it. That makes sense. All right. Internet socket addresses. This is probably gonna be a big chapter, right? Yeah, it's a big chapter, big boy. So this goes all the way to 1235. No, 1237. So we got 35-ish, something like that, pages to go. Let's see what we got for internet addresses here. Internet socket addresses. There are two types of internet domain socket addresses, IPv4 and IPv6. IPv4 socket addresses is the struct sock adder in, and then there's a struct sock adder in 6. An IPv4 socket address is stored in sock adder in structure defined in net inet in.h as follows. So it's just 32-bit integer, but it's big endian. So we got the in adder, and then we got the family, the port, and the adder. In section 56.4, we saw that the generic sock adder structure commences with a field identified as socket domain. This corresponds to the family field in the sock adder in structure, which is always set to AFINet. The SIN port and SIN adder fields are the port number and IP address, both in network byte order. Oh, the port has to be a network byte order too. Okay. The in port T and in adder T data types are unsigned integer types. (16 and 32 bits in length, respectively). IPv6 socket address. Like the IPv4 address, the IPv socket address includes an IP address plus a port number. Difference is that the IPv6 is 128 bits instead of 32 bits. An IPv6 socket address is stored in the sock adder in 6 structure defined in net inet in.h as follows. So that's an array of uint 8, and it is 16 bytes, which is 128 bits. Okay. Socket adder. But now we have this thing called flow info, which is IP6 flow info, and a scope ID. The SIN6 family field is set to AFINet6. The SIN6 port and SIN6 adder fields are the port number and the IP address. The uint8T data type used to type the bytes of the adder structure as an 8-bit unsigned integer. The remaining fields, the flow info and scope ID, are beyond the scope of this book. For our purposes, they are always set to 0. All the fields in the socket in 6 structure are in network byte order. I imagine the family isn't. But port, flow info, scope ID, and adder might be. IPv6 addresses are defined in RFC 4291. Information about IPv6 flow control can be found in Appendix A and in RFCs 2460 and 3697. RFCs so-and-so and so-so provide information about the scope ID. IPv6 has equivalents of the IPv4 wildcard and loopback addresses. However, their use is complicated by the fact that IPv6 address is stored in an array rather than using scalar type. We use the IPv6 wildcard address to illustrate this point. We consider the constant IPv6 in6 adder any init. Excuse me. It's just all zeros. On Linux, some details in the header files differ from our description in this section. In particular, the in6 adder structure contains a union definition. It divides the 128-bit IPv6 address into 16 bytes, 8 2-byte integers, and 4 4-byte integers. Because of the presence of this definition, the glibc definition of the in6 adder and any init constant actually includes one or more set of nested braces than is shown in the main text. It's a lot of braces. We can use the in6 adder any init constant in the initializer that accompanies a variable declaration, but can't use it on the right hand side of an assignment statement. Since C syntax does not permit structured constants to be used in assignments, instead we must use predefined variable in6 any adder any, which is initialized as follows in the C library. So it just takes the constant and assigns it to a bit of memory, a bit of global memory. Thus, we can initialize an IPv6 socket address structure using the wildcard address as follows. So we say, hey, give me a socket adder for in6. We're going to call it adder. And then this says, hey, I'm going to set zeros to everything, which isn't needed anymore because you can use the struct initialization syntax. And then we set that to the any, and then the port we have to convert from host to network. Corresponding constants and variable for the IPv6 loopback address :1 are in6 adder loopback init and in6 adder loopback. Unlike their IPv4 counterparts, IPv6 constants and variable initializers are in network byte order. Oh, interesting. But as shown in the above code, we must still ensure that the port number is in network byte order. If IPv4 and IPv6 coexist on a host, they share the same port number space. This means that if, for example, an application binds an IPv6 socket to TCP port 2000 using the IPv6 wildcard address, then an IPv4 TCP socket can't be bound to the same port. TCP IP implementation ensures that sockets on other hosts are able to communicate with the socket regardless of whether the hosts are running IPv4 or IPv6. Interesting. The socket adder storage. Sorry, I'm on the wrong page here. Socket adder storage structure. With the IPv6 sockets API, the new generic socket adder storage structure was introduced. This structure is defined to be large enough to hold any type of socket address, i.e. any type of socket address structure can be cast and stored in it. In particular, this structure allows us to transparently either store either an IPv4 or an IPv6 socket address, thus removing IP version dependencies from our code. The socket adder storage structure is defined on Linux as follows. So we pound defined an align type uint32t struct socket adder storage, which has a family, the align type, to force alignment, and this padding. Okay. Let's go ahead and break there. I'm going to go take a walk and maybe run to the store. But I will be back probably around 4:30, maybe like an hour and a half, something like that. 4:35, just to get a little bit more reading in. Wanted to get 50 pages done today, but I just don't think that's going to happen. Today was a bit of a wash, but yeah, I'll be back in about an hour and a half to continue reading here on internet domain sockets.